Welcome to Concrete Path. Yesterday uh, we have the different concepts. Among them, one of the concept was that the equality of shear stresses. Equality of shear stresses. Then we said that if a member is there, say a beam, then we took a point at the end at the support. Say was your support. At that support, we said of pure shear case. Pure shear, that is, only shear stress is acting on the plane, no normal stress is acting. So then we took that plane out and we said on that we make a cuboid on that element. The cuboid is like uh, you have three axes. You have three axes: y, x, and z. Then then you say that let's say in the x direction you have sigma x, in the y direction you have sigma y, in the z direction you have sigma z. Now if you make that but actually the point is not in equilibrium. To make it in equilibrium, we make a cube or cuboid shape that represents the state of stress on that particular point A. Then we make a cuboid. Let's say we are making a cuboid. Then we say that, let's say on this plane, sigma x was acting here, and sigma y was here, and sigma z was there. Then to balance that, the element should be in the stable equilibrium. For that, we gotta apply stress, equal stress in opposite direction. Let's say on this plane we apply sigma x in the opposite direction, and uh, sigma y was in this direction, and this was your sigma z in the outward direction to the plane, sigma z. So that's why this cuboid forms. Else this is a point. We On that point we represent the state of stress as a cuboid on which six stresses are acting. There can be actually 18 stresses. If we add tau's also, shared stresses, on this plane there would be tau, on this plane there would be tau, on this plane tau, tau, this way also, and this way also, because each plane has two shear stresses and one normal stress. Yeah. Now coming back to this pure shear case, we have the main concept that we saw yesterday. Uh, that's like uh, wait a minute. We took out an element of that around that point A. We said this is your element. Then we using the concepts of force and moment equilibrium, we were able to say that the if tau is acting on this plane, we say it has tau yx. The tau yx has to be applied in this direction also, in the opposite direction, to maintain the force equilibrium. And but because of this these two, the element is rotating in clockwise direction, so it's not a good thing in civil engineering if something rotates. So we would do we had to there should be some forces that are stabilizing this element. So then from the moment equilibrium, we say that the complementary shear stresses are acting complementary shear stresses are acting and their representation, we have studied how to represent those and their sign convention. We say this one was your tau xy, and for that, if tau xy is acting here, it has to be balanced by uh, on the other face, on the other face in the opposite direction as tau xy using force equilibrium. But then we have from the moment equilibrium, we said that the tau yx has to be equals to tau xy. This was very important conclusion that you have to remember for the further strength of material. Then we have next one, that's your internal forces. Internal forces. All external forces, whatever they may be, there may be moments, there may be there's loading forces and moments. All external forces, moments, they cause because of that there is internal resistance in the deformable materials. So they cause what? They cause internal forces. Internal forces in the member. The internal forces is like, let's say you have a beam, or any structural member. Then we say uh, there are loadings and moments applied. These are external loads and moments. So we say that what is the internal forces developed. Let's take any section. We say take out a section anywhere. Let's take here section. Then we cut and do the free body diagram of that. We say, let's say because of that loading, and we have on this section. This was your section. This one. Let's take this as y, this as x, and this as z. Then we said that in the we had to fix one. Like if the longitudinal axis we say that we can say we can take it as a reference. Say x axis is the longitudinal axis. If long axis is x axis, that means y and z have to be lateral or transverse axes. So in the x direction, let's say you have internal force developed as px, and in the y direction, let's say you have internal force developed as py, and in the z direction you have force applied as internal force developed as pz. And there are moments also developed in the internal section, that are internal forces also. So you have in the x direction you have moment x, in the y direction you are having moment y, and in the z direction you have having moment z. Once you have fixed x as longitudinal axis, we would say um, px is your axial force, or we can say it is your normal. It's a kind of norm is a type of normal force when it's passing through the axis, centroid axis. Next one is where are your py and pz. These are your shear forces. These are shear forces. They are parallel to this plane. They are trying to cut the material into two. That's why the name is shear force. So these are shear forces. For the moment x, this is your twisting moment. It tries to twist the fibers in the longitudinal axis. Because of this moment, the fibers kind of twist. That's why we call it as twisting moment. Then you have moment y and moment z. We call them as bending moments. Bending moments, because these two moments, they try to bend the fibers in the longitudinal axis. Okay, this one trying to bend in the longitudinal axis, moment y, moment z also trying to bend those members. Okay, this was your internal forces. So your internal forces are mainly four. You can have four internal forces. Four. Number one, axial forces. Number two, your shear forces. Number three is your twisting moments. Number four is your bending moment. So these are your four important internal forces. In the next lectures, these would be our main concern to solve for the shear forces, twisting moments, and bending moments. Okay. Next, is your uh, next one is your superposition theorem. Superposition theorem. Superposition theorem. We say we have different. Uh, we have different loads. Let's say we have P1, P2, etc. They are acting initially. They are acting individually. Then we say their effect is say delta 1 and delta 2. Then after that we combine we simultaneously apply the loads together. Then we check the combined effect of these loadings. Then we say that if superposition has to be valid, there has to be some uh, criteria. So the criteria for the superposition term to be valid is that the material has to be under Hooke's law. It should follow Hooke's law. That is, stress should be linearly proportional to strain, as in this initial portion. That is, the loads have to be within the elastic limit, and the next one is your deformations caused, deformations delta or theta. Deformations caused should be should be small, should be so small so that its effect in others loading, say P2, it should not affect the uh, it should not affect on the, if P2 is acting, it should not affect on that because of P1. P2 should not be affected. P2's effect should not be affected. Yeah, this one is your superposition. So let's say you have a beam, this one member, then you applied force P1. We already know what is the deformation displacement delta 1, elongation. Say this one is your elongation delta 1. It's equals to P1 L1 L1 A1 E. This one is your P L by AE. Next one is your same member. Same member, same cross section area and length. Then you apply force P2. Then we say delta 2 equals P2 L by AE. Material is same, E is same. Then now, if you want to combine the effect, let's say in the third stage, length and A is same, you are applying force P1 plus P2. P equals P1 plus P2. Then the uh, delta equals force L by AE. Now, if you want to see that if you sum the summation of delta 1 plus delta 2, that's also equals to P1 plus P2 L by AE. So your superposition is valid only if your stresses are within the elastic limit. That's how, when this has been derived, it was under the elastic limit. Now you have another one for the resilience. We have studied resilience. We have resilience equals half of sigma square by 2 sigma square by E into volume. Resilience, that's also called as strain energy stored in the body, U, represented by the U. That was saying under elastic limit, if the load is under elastic limit up to the maximum point, that is your B, elastic limit point. If the all the energy stored in the material up to the elastic limit is your strain energy. That's called as proof resilience. Proof resilience. That's equals to sigma square by 2E into AL. Now, now this is also in the elastic limit, but we want to see if proposition is valid in the strain energy, in the strain energy. Now, same bar you take. Uh, let's say you applied stresses P sigma, or you applied load P, anything you can say. Length was L, area cross section was A. Then you calculate the strain energy. Strain energy, half sigma square by E, area into length. That's your volume. Now, if you write it in terms of P by A, you say P square by A square E into AL. Finally, you got strain energy equals P square L by 2AE. Strain energy in terms of axial force. This is your strain energy. Important one. So let's say you have applied force P1 or stress 1. So your strain energy 1 was P1 square L upon 2AE. Similarly, for load P2, your strain energy is your P2 square L by 2AE. Now we combine the factor. We say let's apply together the load equals to P1 plus P2. So your strain energy equals P1 plus P2. So it is a function square function. We said in the assumption or criteria that the stress has to be linearly proportional to strain. That is or the load has to be related to the deformation it causes as linear. So P, we know delta equals PL by AE. So delta and P are linearly proportional. So but the strain energy, we have delta, we have that P and U, the cause is P and the effect is strain energy. They are in terms of square, they're just not linearly proportional. We want to see if it is valid now. So proposition is valid. Let's see. P1 plus P2, P1 plus P2 square by P1 plus P2 whole square L by 2AE. Now, if you want to say, let's say U1 plus U2, that's equals to P1 square plus P2 square L by 2AE. But that's not equals to U, because here is square. So square gives you P1 square plus P2 square plus 2 is P1 P2. This extra part, this would go. So your strain energy does not, superposition is not valid here. Suppose superposition theorem is not valid here. Okay, now your main topic in the first chapter was deformation of members. Deformation of members under axial load. Under axial load. Your first case was, you have already we have already calculated that if you have a body of, we said it has a weightless bar. It has no weight. Assuming it has no weight, and you apply force P along the axis, we said that delta equals PL by AE, from the concept of that stress equals modulus of elasticity into strain. Then we have P by A cross section. You have a cross sectional area here. Okay. Then was your cross-sectional area. We said B by A equals modulus of elasticity into strain. Strain was your change in length upon original length, and we got that PL by AE. Now next one is your stepped bar. Next one is your stepped bar. Stepped bars. Let's say this one, you have one bar, then we have another bar connected here, then again we have third bar connected to that. Now these bars are hanging, okay? You have different area cross section, A, A1, E1, L1. You have A2, E2, L2. You have A3, E3, L3. Material is different, so your elasticity is different, and different lengths and area cross section. Now you are applying forces of let's say these are your external forces applied on this uh, configuration. Here it is PB. Here it's here it is let's say PC, and you have here PD. It is A and B, C and D. So I already said that free body diagrams are very important in civil engineering. So we gotta do free body diagrams of these three parts. Let's take one by one. Here is see, there are three forces acting internal, these external forces, and a support is also there. So applying force equilibrium, we say that summation of forces in y direction has to be equals to 0. Then we have, let's say the force in the force in the reaction in the at A, say reaction at A equals reaction A, but in the upward direction. See, it's in upward direction. Then taking positive as upwards, the forces which are in the upward direction, we will take them as positive. Say now from the force equilibrium, we say RA plus PB minus PC, it is downwards, and minus PD goes to 0. This is your number one equation. Then we have another equation that we would say now we want to calculate the deformations, total deformation, delta total. We already know that deformations are equals to the displacement or elongation or contraction equals PL by AE. Then we will say for this one we have delta 1 plus delta 2 plus delta 3. Now we have to calculate delta 1. For that you need to get P1, and for that you need to get P2, and for this you need to get P3. Rest is your L1 A1 by E1, L2 A2 by E2, L3 A3 by A3 by A3 E3. Then you do summation. But firstly you need to know P1, P2, P3. For that, free body diagrams are must. Let's take free body diagrams. This one is your we assumed the direction of reaction A as upwards, RA. This one is your RA. Uh, uh, say there is kind of confusion. You would say why to keep this PB. Either you need to keep it here PB, or we need to keep it outside of that. Why to keep it, or we can say why to keep it. Should we keep it in the member BC PB this way? For that, you can do anything. The structure has to be in the equilibrium. Say take this member, थोड़ा सा dx पहले काटना है बस. This is kind of tool. say dx पहले काटो, मेंबर के एंड होने से पहले dx पहले ही काटना है यहाँ पे. then it's becomes easy. Okay. I would say I would now calculate the, say if the PB is acting at the junction, I cut it before this location where PB is acting. So PB's effect won't come in the free body diagram. So there's no PB here. But in the member 2, there has to be PB in the upward direction. PB. This one is your AB. This is your BC, and third one is your CB. Now we know you have studied like normal reaction. You have two bodies of mass m1 and m2. Then we do free body diagram. We say that on the body m1, because of m2 normal force is acting, and on the body m2, because of m1 normal force is acting. And so at this junction, since we say external force was not there that is applying on the bodies, but internal normal reaction was there, uh, that's equal and opposite in direction, so that to maintain the force equilibrium, if on the one body it's acting in say positive direction, in the other one it has to be in the opposite direction. So similarly, if you are applying Ra in the here is also some P internal forces developed. It has to be in the opposite direction. P internal, that has to be equals to reaction A. To maintain this force equilibrium in this member, Ra have to be this P internal have to be equals to Ra. Now, if Ra is acting on this section in the in the downward direction in this member, because the section is same, this one and this one, yeah, the force, uh, this Ra have to be in this direction also, in this member, opposite direction, because of this normal reaction concept. Now the forces here have to be equals to uh, Ra plus Bb in the opposite direction, and for this member, same, this force have to be in the upward direction, Ra plus Bb. But at the end of the member, you have already there acting PD, or we can say, let's remove this one. We would say here is we would say Ra plus Pb. But from the you can say from the question, we already know that Ra plus Pb is equals to Pd. Direction is same here. This direction and this direction have is same. That is, this value is equals to this value. Both are, say, negative. Okay. So now each internal force you got. This was our main concern here. P1, P2, P3. Now you got P1, P2, P3. You can get delta total. Okay. Now, third one is your bars are bars are of sorry, bars of varying cross section or load. If load is varying and or cross section is varying, let's say this is your cross section, area is also varying. It's a circular uh, rod bar with a capping. So here is diameter D2, here is diameter D1. So it's varying. So your area at any section, area cross section is varying. Or if say load is also varying. Now if say a load is also varying along the axis, we will represent it as P at X. So at X, if X is varying, P is also varying. So we already know the standard equation P L by A T. This is just standard equation. Now there was force Px. Uh, but since X is also varying, area is also varying, we will take any section X, deformation at any section X, we'll say that's equals to Px and area X, but the section have to be smaller section that we have to integrate. Would say take a section dx, that means length have to be equals to dx. Then you have forces here px and px, and area here cross section is ax. Then because of that, this one is your delta at x, delta of strip individual. So there are infinite number of strips in the overall section, overall member. Then you do integrate this or this equation. Would say delta total equals integration 0 to L delta strips integration of all the strips, uh, integral of all those strips, and your length is varying. Px is varying from 0 to L px dx by axe. This is your delta total. This is your standard equation. Now, because of that, you have now solving for the load is varying. Take deflection due to self weight. Deflection due to self weight. Let's say you have bar, but it is not weightless. You have bar. You are not applying any external force P, but the bar is having weight. Say bar is of steel. Its unit weight. Unit weight is gamma. We represent it as gamma. It's equals to weight upon volume. Weight upon volume. Say weight is in kilonewton, volume is in meter cube. You know, density is mass per unit volume, kg per meter cube. If you multiply it with g, you will get gamma. So say unit weight is gamma, and you have length L, area cross sectional, area cross section you have A. Okay. Now you know you have seen you might have done pull-ups. Say this is your frame. Then you're here and you do pull-ups. You do pull-ups. Or you're hanging on that rod. So where is the maximum stresses, or why is the maximum load that is being carried out? If you say Do you feel any pain in your legs? We would say no. Near the legs there is no force, but in the hands, near the hand region, in the shoulder region, you got more and more pain. So your with going upwards, your load is varying, load is increasing at the maximum, and the maximum is at your hands. All the load of your body is being carried out through hands to the bar. So maximum load is at your hands. So this is your variation. Similarly, this is treating the man as this bar, uniform bar, prismatic bar. So your variation of weight would be this one. So at each, you know, at each section, W is varying, so load is varying, P is varying at each section. Take any X section at X. So we can't say directly that delta equals PL by A here. You have to take strip whenever there is any. This is important here, right? Whenever one of these four, one of four is varying, integrate. Yeah, take strips, then do integration. Take strips. Strip is must, then you have to integrate. Then here, see, we want to say now we would take strip at any X. Say here, take a strip dx. Now do free body diagram, cut the section. You have this one. This is your X length and area cross section A, and next one is your dx. Its area is also A. We want to say how much force is being applied on this strip. If you know strip, how much force is applied on the strip, px, then you can integrate, and you know area at x, it's prismatic bar, area is constant, that is equals A, then you can get the total deformation of the bar due to self weight. Now see, the weight is always downwards. For this section, weight is always downwards. The weight of this part equals, we know, weight equals gamma into volume. Gamma into volume. So gamma is here. Gamma volume for this part is area into x. This is your uh, total area, is your area cross section and length. This is your volume. So weight of this part is gamma ax. We write it as now px, because you can take at any x. So if x is varying, p is also varying. Okay. If W is being applied downwards, there have to be internal force of px upwards, so that the force is in there is force equilibrium. Now, if because through the normal concept, normal reaction concept, we say if px is acting on this section here upwards, in the strip it has to be downwards px. Similarly, to balance this, you have to apply px upwards. Now you need to calculate the deformation, total deformation in the strip. Delta strip. Delta strip is your uh, delta strip is your px dx pl upon a x e. Since area is not varying, we would say take it as a. Take it as a. Then we say that px. What is the value of px? Px equals gamma ax. Gamma ax dx upon ae. You got delta strip equals now we will say delta total equals integration delta strips, delta of this strip. If we combine all those strips, infinite number of strips, see, one thing we have ignored, the weight of the strip. Since the strip is, we said strip is very, very, very small, you have infinite number of strips in the length L. There's actually weight of the strip also, but we ignored this weight of the strip for the calculation. We say that delta total equals summation of delta of all the strips. That's equals to integration 0 to L C gamma x dx upon E. So your integration, if you do integration, you would get delta equals gamma L squared by 2E. This was for a bar for which cross section is not varying. Area cross section is constant. That's prismatic bar. Along the length, area is not varying. Area cross section. So it is your delta equals gamma L squared by 2E. If you represent it in terms of uh, W, total weight of the body, we know, we'd say weight equals gamma into volume, and gamma into volume. Volume is your area into length. So if you substitute here gamma, so gamma is your, so delta equals gamma. Gamma is your W by AL, L square by 2E. So your deformation is WL by AE. This one, WL by 2AE. Can you see the difference between the bar that was weightless and force P was applied? Say the weight of the body is P. Say the body weight is P, PL by 2AE. We know already that the deformation for the, if P load was applied for the if self weight was not there, we say it is weightless. Deformation was PL upon AE, but for the bar, that's that's weight which is having self weight of W equals, say P, your deformation is P L by 2 AE or gamma L squared by 2E. But see the difference in this one. If you cut any section, if you say add any x, your P is not varying. Take any section, say this one. If you cut this one, this part of the member, if P is applied here, it has to be balanced. For this part, P is applied here, it has to be here P. Then in the member, this part, it had to be P. It had to be P. For the upper part, it had to be P downwards, and reaction would be upwards P. So every member is having load of P, and if area cross section is same, so your stress at every fiber is same. At every strip, stress is same. So if you plot the variation of that load, it would be like this one. But for the first one, we saw it was triangular variation. Okay. So if you take a problem, it might come in an exam. Say you have a body here. It's having self weight of P, and you're applying force of P here, and length is L, area cross section A. Get the total deformation. Now, can we use superposition theorem? Yeah, we can use superposition theorem. We know P is linearly proportional to the effect it causes. That is your deformation, delta displacement or elongation contraction. So we can say delta equals, for this part, external force P, would say deformation equals PL by AE, and for the self weight we would say PL by 2AE. Then self weight can be anything. It's like general equation for that. Next one is your next one. Next one is your tapping bar circular cross section. Circular bar of tapping cross section. Cross section. It's like uh, it's like this one. Like a cone, you can say. Here the diameter is say d. Here is diameter 0 in the length L. This is your length L. At each x, say at any x, you take strip. Why take strip? Because your area cross section is varying. If any of the four those parameters is varying, we take strip. So this is your strip dx. Now taking the strip, we would say let's say this one, calculating the forces on this part, that's equals to weight of this part is downwards, weight of x equals uh, total length is x, weight of this part is gamma into volume. Gamma is gamma of the material. It does not depend on cross section. Gamma into volume. Volume of this part is, we know volume of cone. Volume of cone is area into length by 3. Okay. Your area is at the top. This one. They add say the area, say the radius at this section is rx, or diameter is dx. So your weight x becomes gamma pi rx square x by 3. Now see, for the dx strip, ignoring the self weight of the strip, we'd say this is your dx. If p is applied here, if wx is acting downwards, there have to be balancing there have to be someone balancing that. It is internal force px equals wx. Same px would be here and here px. So delta strip is your px dx ax e. Okay, since we know in the px wx was wx was equals to px, so that the forces are in equilibrium. Px equals wx, which implies then we have px value of px was gamma ax by 3. Dx upon ax is also here. So your ax and ax gets cancelled. We can have gamma x dx upon 3 e delta strip. So the total delta is your integration 0 to L gamma x dx upon 3e, that equals to gamma L square by 6e. So if you write it in terms of weight of the body as W, we know weight equals gamma into volume. Gamma into volume. Volume is your A into L by 3. So representing it in terms of weight, gamma is your 3W. Gamma is your 3W. 3W 3W by AL into L square by 6E. That's your WL by 2AE. Same as we observed in the prismatic bar. having self-weight W. Now, next one is your same bar, but it's not up to the end. It was tapering, circular section was tapering, but you stop it to a point where the diameter was D1. Actually, at we studied this one, diameter was 0, but for this case, we were stopping up to D1. The diameter here it is D2, and length L, this is your length L. What is your length L? Okay, so it's you are having self weight of W and this gamma unit weight, and uh, we know we can have we need to find the deformation delta for this bar. How can we solve this? We know already we solved for this bar. We know gamma L square by 2e is your total deformation. We can use superposition theorem here because delta is linearly proportional to the weight, so we can use superposition theorem. Let's say this hatchet part is L1. We can say the total deformations of this part, total deformation of this part, delta total of this part have to be equals to, if we calculate initially the deformations of overall this part, overall gamma, write it as, say we write it as A, say we write it as A, B, and here is C, D, E. We write it as delta of A, B, E, but actually this part C, D, E is not there, so you need to subtract the deformation of that part. You need to subtract the delta C, D, E, and also you need to subtract one more thing. That's what is the main critical point in this question. Delta more. That more we will see. We know we solved. We said we took one question. We said let's say you are having a bar. Its self weight is W, and you are applying external force W. The total deformation was WL by AE and WL by 2AE. So you imposed the two effects. Similarly, we had to impose the effect of this part, the external part which is not there, this one. Its effect as an external load. Its weight is W. Its load as external load acting on the overall actual length L. That's that delta more. Understanding the point? Okay. See, here if you represent that variation of weight, we would say initially we would say the self weight is like that. Maximum at W is at here and 0 here, and because of the external load, each dx is also having self weight, external weight of W. So you are at the top, you are having W plus W, and here you're having W plus 0. This is your variation of weight or force in strips. So that's why here you have to subtract delta more. So for the first part, delta ABE equals AB ABE equals gamma L square by 2e, okay, minus delta CD. For this part, you also know deformation, you know, gamma L1 square by 2e minus. Now the main point is here. We know formally a body is here. You're applying force P. You need to get the deformation in the member. So it's Px. It's P L by area E. Area has to be something. We know one more result is like if the diameter is here d2 and diameter and it is tapping bar, circular bar, and diameter here is d1, then you apply axial force of P, then the deformation uh, equals P L by area. Area is your pi by 4. We say d1, d2, and E. We will be solving this one also, but for this question let's take the result directly. We know deformation equals PL by AE, but say now we need to calculate the value of P. The P value of P is the weight of this part CDE. P we write as PCDE. PL 1 PL by AE. So firstly, we would say what is the value of E? The value of E comes out to be pi by 4 d1 d2, and the PCDE equals, its weight of CDE, that equals gamma into volume. Volume is your 1 by 3. Volume is your 1 by 3. Area at the top. What is the area at the top? Area cross section. Diameter here is d1. So your area becomes pi by 4 d1 square, pi by 4 d1 square into length 1 L1. This is your volume. So yeah, let's solve it further. Let's say the delta total equals gamma. If you simplify this one, you would say gamma by 2e. Can take it common here. Let's say L1 square, L square plus L1 square plus twice L1 L minus L1 square minus, you have PCDE is your gamma pi d1 square L1 by 2L, and length is your L, area is your pi by 4, pi by 4, pi by 4 d1 d2, and area is your E. After simplifying, and you would be getting the result as delta total equals gamma L square by 6e, 1 plus twice diameter 1 by diameter 2. Diameter 1 is your smaller one. Diameter smaller, diameter larger. We know if say the tapering was such that the diameter 2, say the diameter 1 was equals to 0. If you use here diameter 1 equals to 0, you would get gamma L square by 6e was your initial result. Okay, next one. Next bar, Next bar is your cross-sectional area is here A, and is a square bar of varying cross-section, right? It's the headline for this square bar of varying cross-section. If the cross-section, yeah, varying cross-section. So if the area of cross-section is varying, so we need to take the strip, then we do integration. Say this one. Uh, let's take a bit downwards. See, at this section, your square cross section is A, and at any after the length L, your cross section becomes let's take F. Here. It becomes B, and here was AA, was AA. Then we join them. In the length L, your area cross section varies from A to A square to B square. So taking the strip at X from A, would say taking strip at X from A, would take out a strip. One is your strip dx, taking out a strip dx, and you apply force. Actually, initially you had applied in external force of B. So you need to calculate the total deformation in this bar. So calculating that, you took out a strip. So in the strip, you have this one is your strip of length dx, force is applied B, and force applied B. But the here the area of cross section is something different. It is more than A square and lesser than B square. We need to get the value of, if we get the dimension of this, say the dimension, and here is uh, let's take A1. Dimension here is A1. So your cross-sectional area at X becomes, so your AX becomes A1 square. Area at X becomes A1 square. Yeah. Now we know standard result, delta equals PL by AE. So we would take a strip. Let's take that strip. Then we do delta strip equals P is constant. It's not varying with the length. So P is constant. Taking the strip dx, your area becomes area at X, and your E is constant. So firstly, you need to get the value of A1. The your area cross section is varying from A to B in length 0 to L. So we can do a linear interpolation. We will say uh, value of A1 is equals to A plus the change of side is change of side in the length L is B minus A upon total length, and up to that moment you want, that's your x. This becomes your side value of side at ax. So your ax or a1, we can write it as ax, taking at ax. Ax becomes a plus, taking b minus a by l as some constant k x. Now we will be using in the equation. So your delta strip becomes b dx by area x was your a plus kx whole square, a plus kx whole square into e delta strip. So delta total, calculating for the delta total. So your delta becomes integral p dx by a plus kx whole square into e 0 to l. If you integrate it, you will get, let's say, integrating it, you can get p dx a plus kx into internal is your k e e. We have a plus kx whole square, let's say 1 by, now substituting the values, substituting the value of a, we would get minus p l by a plus b minus a by l, and you need to apply the value of x as l, 0 to l, for the value of x. Would say value of x is here becomes l into 1 into 1 by k. K was your a b minus a upon l. E, e. What we get, minus b l square. Oh, crazy. He was actually once, only once. You got pl square a plus b minus a. Oh, no way. Really, just calculate it. When you calculate the values, do integration, would say it becomes you need to use both the limits. Okay, minus pl by ke and 1 by a plus k into upper limit is your l minus 1 by a plus k into x. K into x is your 0. Becomes like that. Then we have minus pl k. K is your b minus a upon l. E 1 by a plus b minus a by l into l minus 1 by a. This cancels, a and a cancels, it becomes a minus b by a b pl b minus a minus, and you have e also. So your deformation becomes delta equals pl upon A, B, E, final deformation. Try it yourself also. I got stuck once. Integration. Now you have another one. Tapering bar of constant thickness but increasing width. Tapering bar of constant thickness. Thickness is constant, E, but increasing width. But increasing width. Say from A to B. In the earlier one, your T was also varying so that it becomes a circular cross section. Now your thickness is constant. Let's say your thickness is constant. This is your thickness. Its thickness is T, and but the your width is varying. Say your width, write it as this way. Say the width here is A, and at this section width is, say the width is here B, so your A is width here, and width is changing to B when you move to length cal. So since your area cross section is varying, what you need to take? You need to take strip, taking any strip. Let's say at an X from A, you take a strip, this one. Suppose the dimension here is, suppose the width here is AX. Sorry. You take strip DX, and the dimension here is width at X equals, I will write it as AX. So your formula delta equals P. P is constant actually. You apply force P here, P here, P. P is not varying with the length, so P is constant. You take strip dx, delta strip upon A. Area cross section is your AX square. No, area at this section is your width into thickness. Width into thickness. AX into T into E. Now you need to get the value of AX. Value of AX is A plus change of thickness B minus A per unit length, total length, but I need only for the value of X. Say it is write it as B minus A plus KX. A plus KX. Your A becomes B minus A by L. A plus KX. Let's go. Where delta becomes 0 to L, B dx. Your A was A plus KX into thickness into modulus of elasticity. So you're solving this equation. We have equation integral. Yeah, solving. I will write as dte integral 0 to L dx by A plus kx. So your function is in terms of x, and you are integrating with respect to dx, so it becomes d by te ln of A plus kx, and your limits are from 0 to L. So your deflection becomes P by TE ln of A plus Kx, A plus K into X. Your K value is B minus A by L into X. Value of X here you had to use as L minus ln of now your lower limit is 0, so we would write as ln of A plus K into 0. That becomes 0, so your ln it becomes ln A net. So your total deflection becomes P by TE ln of A plus B minus A. So it would become as B ln of B minus ln of A. We can write it as P by TE ln of B by A. But the thing is, we missed something. We missed something. Yeah, what we call as internal differentiation we missed. Because A plus Kx, yeah, this one in the function here was A plus Kx, so you have to divide overall value by K. So you have to have here K, here K, and here K. What is the value of K? The value of K is uh the value of K was A plus yeah, B minus A by L. B minus A by L. B minus A by L. This was the value of K. So your equation becomes delta equals PL by B minus A DE ln of B by A. Or you can write it as EL ln B minus A by B minus A DE. One or this one. Result is very important. Now this topic has been finished. Now our next topic is your rigid body effect of rigid body movement. Effect of rigid body movement. Let me go firstly to the top of this screen. Yeah, it's okay. Let's write a new topic. That's your effect of rigid body movement. Effect of rigid body movement. Let's say you have a bar. Yeah, taking rectangle. Let's say you have a bar. Say the three bars and the connection is free. Taking this one here. what's happening. Okay. The connection between the bars is, I would say, it's rigid. So you are connecting the three bars by another bar that's rigid. That's making them rigid connection. I would write it as rigid connection. Okay. Say this is resting on some support. This one is also resting on some support, but this one is your freely, and you apply force P on the middle bar. Write it as, I would say, this one is 1, this bar is 2, this bar is 3. What's the effect of rigid body moment? If you say the force is applying on the bar 2, it would elongate because the force is tensile, so the bar will elongate. So your deformation in the 2 becomes delta 2. But what about the other part? So for that we need to do free body diagram. So if force P is acting on the bar 2, I would write it as, this is as bar 2, force is acting P, so here it has to be equals to P. Now if the force here is P, then in the bar, that rigid connection bar, you have this one. It's connected to member 1, rod 1. So here firstly we would say, what's the at the mid part, this part, what's the reaction that has been transferred to this point. I would say, if here it's P, then it had to be downward P at the mid. It is L by 2, L by 2. So your force in the bar 1 have to be opposite to that. I will write as P by 2 and P by 2. If the force in this connection is P by 2 and P by 2 upwards, so in the bar 1, I would write as, wait a minute. Wait. In the bar 1, you are having this one is your bar 1. If force is in this section P by 2 upwards, in this part it had to be downwards P by 2, and the support is would give you reaction of P by 2. Same thing is also valid for your bar 3. Okay. Sounds great. Bar 3. So so the we need to calculate the deformation in the bar 2. Say it's point B. You need to get total displacement of point B from its initial position. Say initial position was here. You need to get the B, delta B total. I would say delta B total is deformation in, because of the force in 2 and because of the effect of rigid body, because of the delta 2, I would say rigid body, rigid connection, because of the rigid connection. Delta in B because of rigid connection. So your rigid connection says, rigid connection says, if your bar 1 it's getting compressed, it's compression minus, so your length gets shortened, and for this one also length gets shortened. If this member is getting shortened and support is here down at the bottom, and support is here also at the bottom, and you are having a rigid connection, and third bar is also here, if if the members in the bar 1 and bar 3 are getting compressed, there is no option, इनको ऑप्शन ही नहीं है इसके कि इनको compress होना है, and this point, this joint have to go settle downwards by delta B rigid connection. delta B rigid connection. इनको ये compress मतलब ये actually the deformation delta B RC that's equals to this one P by 2 the length of bar L1 is equals to length of bar L3 PL by area 1 or area 3. I would write that A area is take area is same for the each bar and material is also same. I would write as P by 2 L by AE. This is your compression. This is your deformation. So by this by this amount, your joint at this part, this one, it would go down. Now same thing is valid for the bar 3 also. Now if this joint is moving to this point and this one to this point, so for the member 2 there is no option for this joint else anywhere it can't go except that it has to settle by the same amount because of the rigid connection. Rigid connection does not allow any deformation to happen. Either it can go downwards, it can go upwards, or it can remain straight. But if since this one and this one ends are straight, that means middle one it has to be straight. There's no option. There is no other option. It can't go like this or it can't go like this. Understand? And additionally, the deformation in delta 2 is also there, but since the support B is not fixed, so it would also elongate. This is elongation. In the bar 2, it has elongated by delta 2. So your point B was here. Say the bar actually the wait I will do the point B was somewhere here. Now point B was actually here somewhere. This was your point B. So it has gone under deflection of this one delta 2 plus delta B rigid connection, and this is your concept. Let's take one problem on this question, on this part. Question, problem. You have the middle bar is of copper. Okay, middle bar is of copper. Middle bar is of copper, and you are applying force of 180 kilonewton, and the bar 1 and 3 are of steel. So this is your rigid connection, or this one is of steel, this one is also of steel, and this is your support. These two are of steel. Now copper has a length of 2 meter. Your copper is having a length of 2 meter. Length of copper is 2 meter. Copper bar is 2 meter, and length of and for each steel post height is 0.5 meter. Height is so your length is 0.5 meter length, and area cross section of steel post is your 4500 mm square area steel, and area copper I would write as area cross section of copper, that is your 4800 mm square, and the modulus of elasticity of steel, that is equals to 200 gigapascal, and modulus of elasticity of copper is your 120 gigapascal. So the question is, a long rectangular copper bar under a tensile load P hangs from a pin that's supported by two steel posts. Then you need to determine downward displacement of downward downward displacement of lower end of the lower end of copper rod, copper bar, lower end of copper bar. This one. Say the point is B. You have to find the downward displacement of this point B because of the load 180 kilonewton. So we already do the analysis of this part. We can say directly now. Actually, you need to calculate the deformation. You need to calculate the initially what I already have told you. You need to get the free body diagrams. We know we can say in the steel. See, in the steel, I would say this was your copper. This is your 180 kilonewton. Same have to be here 180 kilonewton, and same have to be applied downwards 180 kilonewton. And your length is same, so L1 and L2 are same. So your force in copper in steel bar 1 is your 90 kilonewton, and here is also 90 kilonewton. And for the steel post, your 90 kilonewton is compressive in the steel bar. Here it is tensile, and here it is compressive. So your steel posts are getting compressed 90 kilonewton. So your for the concept of rigid body displacement, I would say delta downward of B equals this one delta because of load in copper plus delta because of one and because of steel and rigid body displacement. Rigid body displacement. So your delta because of P in copper is your tensile force. So it is your P 180 kilonewton. 180 kilonewton. I would write it as 10 to the power 3 Newton. P L is your length of copper bar. That's your 2 meter. So writing as 2000 mm. 2000 mm. By area cross section of the copper bar, that's your 4800 mm square. And E of copper is your 120 gigapascal, writing as 10 to the power 3 megapascal. Megapascal is your Newton per mm square. Gigapascal is 10 to the power 5, 10 to the power 9 Pascal, and this also equals 10 to the power 3 megapascal. That's also equals to 10 to the power 3 Newton per mm square. We will be writing each of these quantities in terms of Newton and mm. Your final deflection is like 10 mm, 20 mm, plus 5 mm, like that. So that's why we will be calculating in terms of mm. This was your point B getting stretched under the effect of 180 kilonewton. So it was positive tensile force, and uh, uh, in the since the force in the in the steel bars is compressive. So these members, the fibers have to go down by this delta steel. Same have to be here delta steel. Now your rigid connection is shifted to this part, and this connection has shifted here. So for this connection, it has no option other than to also reach to the same level. This one. So your point B. So this part has been shifted downwards. So your point B has also shifted downwards by this amount delta steel, and already it had been stretched by delta copper, this one. Okay, so your next one is your delta because of steel and rigid body displacement. That's equals to deformation in the steel. I would write as 90 kilonewton. 90 kilonewton. Length of the steel post was 500 mm. This one, 500 mm. Area cross section 4500 mm square into E. E was your 2000 gigapascal, 2000 into Newton per mm square. Calculating the total deflection, it comes out to be 0.75 mm. 0.675 mm. It is the downward displacement of the lower end of the copper bar. Next question is saying, the next part of this question says, get the maximum delta maximum permissible. What should be the maximum permissible deflection if the, yeah, what is the maximum permissible load, maximum load that is permissible if delta maximum is limited. If you want to say that the deflection should be limited to 1 mm. Yeah, we know for the force of 180 kilonewton, you got deflection of total 0.675 mm. So for a deflection of total 1 mm, you can use superposition. Can we use superposition here? You can say P and delta are linearly related. We can say for P equals 180 kilonewton, your deflection was 0.675 mm, and for deflection to be 1 mm, your load has to be equals to 180 kilonewton per 0.675 mm into 1 mm. That comes out to be 266.67 kilonewton. Or you can also calculate this way also. You say, let's take, you can also, if the question is like conventional, be a 20-mark question, you can say, now in the part 2, it's taking the force, maximum force as P, you can get deflection 1 as P L by AE. Rest is constant, P L by AE, and plus this one was your P by 2. You can write it as P by 2 L by AE. And final deflection, you already know here. You already know that the net value is 1 mm. You can get the value of P. That way you can also solve. Next question. Next question. Rod ABC is made of aluminum. Rod ABC, you have separate bar. This one, this part is 0.4 meter, and this part is your 0.5 meter. This is A, B, C. Forces are, here force is applied P, here force equals Q. These are your external forces. Q, the value of Q is 42 kilonewton, and the value of P is your kilonewton. And material is aluminum. aluminum. Modulus of elasticity of aluminum is your 70 gigapascal. We need to get the deflection of point A and deflection of point B. Get the deflection of point A and deflection of point B. Deflection of point A and deflection of point B. Okay. See, at point C, there won't be any deflection because the point C, at this point, support is fixed. Point C can't move anywhere. The point C is fixed. That's why the question is saying delta A and delta B only. So either the materials are getting compressed or getting elongated. That's that we can get from the free body diagram whether overall material is getting elongated or contracted, so that we can get delta 1 and delta 2. We would be doing free body diagram analysis. We would say, let's say you have AB, here the force is P, value of P is equals to 6 kilonewton. Value of P is equals to 6 kilonewton, writing in terms of kilonewton. I would write as 6 kilonewton. Yeah. So the normal direction, so the force by force equilibrium here, it has to be equals to 6 kilonewton. Just dx before B, just cut dx earlier. Okay. So to avoid the effect of Q in the first part. And for the BC, you have Q acting. Q is acting, implies here it has to be Q. It is compressive, here it is tensile, positive, it is compressive, and the effect of this 6 kilonewton in the BC is also, it has to be there. If it is compressive here, it had to be tensile here, 6. If it is tensile here, it had to be tensile downwards here, 6. So the net here is taking, I would take as overall net is tensile. Taking net as tensiles, I would write as this way: 6 minus Q and 6 minus Q. Taking the deformation as tensile, positive. I don't know the value of Q. We have another force equation, that P plus, we know that P plus Q, P plus Q. Now P is upwards, P plus Q is downwards. That assume the reaction at C equals upwards, RC plus RC equals 0. We know the value of Q. We don't have to keep it as Q. We can use the value of Q directly. What is the value of Q? 42 kilonewton. 42 kilonewton. And here it's also 42 kilonewton. 42 kilonewton. So the net value becomes minus 36. Minus 36. It means minus means the direction you assumed that the force is tensile acting on the member BC, but the force is negative, means force is acting compressive. So we can get the deformation in AB. Deformation in AB, we can say deformation in AB is PL by AE. P is your 6 kilonewton. L length of the AB is your 400 mm. PL by AE. Area of cross section of AB, we forgot. Let's take area of cross section. Yeah, 20 mm diameter and 60 mm diameter. Pause. Your diameter is 20 mm and diameter is 60 mm diameter. So your area of the smaller bar becomes pi by 4, 20 square mm square into Modulus of elasticity was your 70 gigapascal. 70 into 10 to the power 3 megapascal. So this is your, so the member AB have been stretched by this amount, that comes out to be equal to it has written in terms of 109,135 10 to the power minus 6 meter, or we can say 109,135 0.109 135 mm. This is your elongation in the member AB. For the member BC, you are having compressive force of 36 kilonewton. So deformation in BC equals minus 36 kilonewton. Minus means it's getting compressed. I would write as minus 36 kilonewton. Length of the member was 500 mm. PL by area of cross section. Area cross section was pi by 4 60 square. 60 was your diameter into modulus of elasticity was 70 into 10 to the power 3 megapascal. So your deformation in BC becomes equal to minus 90.947 10 to the power minus 6 meter. You can use it, you can convert it in terms of millimeter. We can say minus 0.0947. 90.947 into 10 to the power minus 6 into mm. Yeah. See, calculators are very important. If you are a civil engineer, you have to got two calculators to see which one is accurate, giving best results. So calculator is very important. You're not a civil engineering student if you don't have a calculator. Don't beg from others. Civil engineering students have to have one at least calculator. I have got two. Okay. So this was your see, we reached here. I would say this was your point C, was your point B, and this was your point A. See, the AB have been elongated by 0.109135. If it has been elongated, it can't go downwards. It can't go downwards. Now, actually, we would say firstly, what's the deformation in the delta BC? That's minus 0.09. Means BC have been compressed. So if BC have been compressed, it would go downwards. So your B gets downwards by this amount. So your B have been displaced to this part. So now this B becomes here. So your B delta, this is your deformation here. So if the B have been settled by this amount, so this part AB have to go downwards by the same amount. Okay. This part is also delta BC. This is your A. But we can use superposition. Now combining the effect of deformation of AB itself, also delta AB has been elongated by plus 0.109135. This one, it have been also elongated by this part. So I would say final deformation, say this effect was because of change in the position of B, but AB is also getting elongated by amount of plus 1.01, this one जो भी है. So it's more than this part. So AB is getting A is getting stretched to a point more than this value, more than delta BC. So the net displacement of the A from the initial position would be this part, delta net at A. I would say delta net at A equals delta AB upwards. Delta AB would be tensile upwards, I would say, and delta BC, that's downwards. So net becomes, net displacement of point A is your, that's your 0.101, 0.109135 mm plus this one is your minus 0.0990947 mm. So final displacement of point B, point A is your 0.018 0.01819 mm. And the displacement of point B, it's easy. This delta BC have been shortened by amount of delta BC equals to minus 0.09047. B is not, since C is not going anywhere, so your delta B equals delta BC equals 0.09047 mm downwards. This was your question. Next one. Next one is your next example. You have a horizontal rigid beam, horizontal rigid beam ABCD. This beam, you have a beam ABCD, A, B, C, D are supported by vertical bars BE and CF. Here you have vertical bar of BE and CF. It is connected. The length of this one is your 3 meter, and length of this one is your 2.4 meter. Now forces, external forces are applied at point D equals to 360 kilonewton, and here at point A force of 400 kilonewton. The length AB equals 1.5 meter. This one is your 1.5 meter, and this one is your 2.1 meter. The total length of the bar horizontal rigid beam, since the beam is rigid, okay, total length is this one, 1.5, 1.5, 2.1. So how can we solve the question? Go for the free body diagram. It's whenever you have some, think of free body diagram. Whenever question becomes difficult to understand, see if we can do the free body analysis. That taking out this rigid beam. Say this is your rigid beam ABCD. Force is your 400. Here it is your 360. Length is 1.5. This one is 1.5. This one is your 1.2.1 meter. Let's say force in the bar BC would be something somewhat say I would write as force in the bar BE, and here I would write as force in the bar BF. I have assumed direction of these two as upwards. Okay, upwards. I have assumed both the directions. So we can say now we need to calculate two forces. If we calculate summation of moments at any of the 2 points, we can get the value of other. Say taking the summation of moments at point B equals to 0, I would say keeping clockwise as positive, clockwise moments about B as positive. The effect of 360 kilonewton. This is your clockwise into length. Length is your 2.1 plus 1.5 meter. And FCF is acting anti-clockwise about this point, this way, anti-clock. FCF into 1.5. And because of this 400 kilonewton, it's also acting anti-clockwise, so we need to keep it negative. 400 kilonewton into 1.5. So the net value comes out to be, we have to keep it 0. So the value of force in the bar FCF have to be equals to 464 kilonewton. 464 kilonewton. And similarly, we can say by the conservation of force equilibrium, we can say FC. No, I would say I have calculated FBE. I would say FBE comes out to be 296 kilonewton. 296 kilonewton, and FCF, we can say we can do also summation of moments about this point now to calculate the O and G. Actually, I have calculated I have calculated the value of I have calculated the value of I have calculated the value of this. I have applied the moments summation of moments at B equals 0. This one, so I would get the value of FCF. That's equals to 464 kilonewton. So you can now get the value of FBE if you apply summation of moments about point C equals to 0. We can get the value of FB, or we can say by equilibrium of forces in the y direction, you can say downward force was your 400 plus 360, and upward reaction was because of that FBE 464. You can get the value of FBE equals to 296 kilonewton. Kilonewton. So once you got the forces F1 and F2, these forces are applied in the bars, these two bars. These bars are made up of material. Their details are shown. So now I would say, since you got the forces, you got two forces. Let's take these two bars now. If this bar is your 3 meter, if this bar is your 3 meter, and force here it is FBE upwards, so in this part it had to be compressive downwards. FBE equals to 400. FBE equals to 296 kilonewton. Yeah. Length was your 3 meter. Area cross section was your area cross section of BE is your 11000 mm square, and E is your 200 gigapascal. Both are bars of steel. E steel. Both bars of steel, and your modulus of elasticity is 200 gigapascal. So the shortening of the bar BE, we can get the shortening of the bar BE, shortening of bar BE, shortening of bar BE. It has been shortened by amount of delta BE equals to PL by A. L is your 3000, PL by A, area 11000, E is your 200 into 10 to the power 3. Units, I already show you how to get the units. Okay. Net value is using net value of mm. You can get the value of 0.4 mm. And similarly, in the bar FCF, in the bar CF, length of the bar was 2.4 meter. Length of the bar is 2400 mm. Area of the cross section, area cross section of CF was 9280 mm square. This is your area cross section, and E already know steel 200 gigapascal. If the force in the rigid beam is FCF upwards, it had to be downwards in the bar CF. Yeah. So this is also getting shortened. So shortening a bar CF can calculate as delta CF equals to, or I would say, force of FCF was your 464 kilonewton. So I would write as 464 kilonewton into length was your 2400, area was your 9280, modulus of elasticity is your 2, Young's modulus of elasticity is your 2 into 10 to the power 3 mm. You can get the value of delta CF equals to 0.60 mm. Shortened. If the bars are getting shortened, where they can go now? If the bar BE is getting shortened, here the support is hinged. It won't allow any movement downwards at point E. So if the bar B is getting shortened, so B point have to go downwards by an amount of, you solved deflection in point BE. Delta B is your 0.4 mm. If your B goes here by amount of 0.4 mm, and CF have also been shortened to 0.60 mm. So if C have been displaced by amount of 0.60 mm, can you get the value? Now the question was, now the questions were, question was that get the vertical displacements of delta A, delta D. Get the value of displacement of D and delta displacement of A. Already we know displacement of B and displacement of C. Since the bar is rigid, if point B is going downwards by an amount of 0.4 mm, this is your point B, it's going 0.4, and point C have reached to 0.6 mm, this is your 0.4, say from this point, reference point, this was your reference point, this one. From this reference line, point B have been shifted to 0.4 mm downwards, and point C have been gone down by 0.6 mm. Since the beam is rigid, it can't bend now. Okay, it had to be remain straight. To maintain the continuity, I would say point D have to go downwards by this delta D, and point A have to go upward. Now I would maintain the continuity. I would say this is your delta D. No, this was not your reference line. Was not your reference line. I would say it. Yeah. The point B have been shifted by amount of 0.40 mm. Okay. If the displacement in point B is 0.4 mm, okay, I can see what should be the value of displacement at A. Okay. Keeping it aside as of now, see, in the BC, your length is 1.5 meter. In the BC, this is your B, this is your C. For the BC member, your length was 1.5. So a variation of from 0.6 meter, 0.6 mm to 0.4 mm deflection in 1.5 meter. So your change is 0.2 mm. So 0.2 mm, the line is changing 0.2 mm per 1.5 meter. So, the line had to be remain straight. If the point A was at a distance of 1.5 meter from B, so the change in this length is also 0.2 mm. It is also equals to your length is 1.5 meter. This one is also 1.5 meter. If point B have the point, say the net deflection between B and C is your 0.2 mm. 0.2 mm. So if the net deflection between B and C is 0.2 mm, for the slope to remain continuous, that the deflection this deflection have to be 0.2 mm downwards. So your point B, point A have to be somewhere here. This is your point A. So your net deflection here is 0.2 mm. So this is your rigid beam. You can make it as a rigid beam like this. This is your rigid beam. The reference from the reference line, center line, the bar at A have been displaced downwards by an amount of 0.2 mm. So delta A equals 0.2 mm. And delta B equals 0.4 mm, delta C equals 0.6 mm. Now, to calculate the value of delta D, we can say from the similar triangles, we can say, see, here the length is 2.1 meter. So we can calculate the value of delta D. We say that line is changing 0.2 mm, or we can say 0.2 mm, gradient is 0.2 mm downward shift per 1.5 meter for 1.5 meter length. But if I need to calculate for the entire length, we say 0.2 mm, 0.2 mm per 0.2 mm per 1.5 meter length. If you need to calculate for the entire length, you would get delta D. So your delta D goes to 0.2 mm per 1.5 mm into 1.5 plus 1.5 plus 2.1 mm. That comes out to be 0.88 mm downwards. Was your question? Now next one is your statically indeterminate problems. Till now we have studied problems that were having supports, reactions, such that we can use the those equation of static equations, that is summation of forces, force equilibrium, summation of forces goes to 0 in horizontal direction, summation of forces in y direction goes to 0, summation of moments goes to 0. So we have used the if the structure was able to be solved using the equations of statics alone, we say that the structure was determinate. Now for the indeterminate problem, you have less number of equations. But the reaction unknowns are more. So you need more conditions to satisfy in order to get the unknown reactions. So we have concept compatibility conditions. Compatibility conditions here. Compatibility condition says unknown forces, or known deformations correlation. Deformations correlation. That is, you know delta and theta at any support, and you can get the force at that support reaction. You can get the reaction at that support. We'll see. Let's say you have a stepped bar. Here it is supported. Here it is support. That is fixed support. We call it as fixed support bar A, B, and next bar is your BC, and it's also supported. So then you apply force P, external force P here. P. So earlier we were solving questions like this one. We said this one. We said if force P is here, I can cut the section, get the value of this one, and get the value of this one. But here you're having. I will show what free body looks like here. Let's say here the reaction is RA. Reaction A is RA upwards, and here is also reaction RC upwards. I would say summation of forces in Y goes to 0. I would say RA upwards plus P downwards plus RC upwards goes to 0. And we can't use summation of moments goes to 0 because they are all three are in the same line. So we can't solve for mz, and fx, summation of fx also 0. There's no horizontal force, so we can't use this equation. So your one equation, that is summation of fy equals 0, only one equation of static is available, but your unknowns are two. Your reaction A and reaction C, your two unknowns are there. So but if you use the compatibility condition that says the unknown forces, unknown reactions, or known displacements ka relation. Do we know displacements here? We can say the net displacements at C equals to net displacements at A, both are equals to 0 because these are fixed. Point C can't move anywhere and point A can't move anywhere. So net deflection at C and net deflection at A equals to 0. If we use this one, we can get the value of reaction A and reaction C. Yeah. Let's say doing the free body diagrams, making free body diagrams. Let's say here the reaction is RA और इसमें dx पहले ही थोड़ा सा काटेंगे तो यहाँ पे आपका reaction RA निकलेगा. RA length is L, say length is L, area cross section A, whatever it may be, L1, A1, and for the bar 2 we have force of P2 here, we have force of P here, and also reaction A in the upward direction. So net, we will say, let's take net as compressive. This one is your positive tensile. Taking net as compressive P minus RA. So we can get total deformations in the bar 1 and bar 2. So delta AB I can write as A, B, B, C. Delta AB equals to positive RA L1 by A1E. And delta BC was your minus compressive P minus RA L2 by A2E. So suppose the deformation delta AB equals 5 mm positive. Delta B has to be minus 5 mm in order to in order to satisfy this equation, that net displacement at C, net displacement at C, or net displacement at A have to be 0. So if we follow it, we would say applying compatibility condition. This is your compatibility condition. Compatibility condition says delta AB plus delta BC equals to 0. Net deflection of the entire structure is 0. Let's say this gets let's say AB gets elongated by amount of delta. It can't go upwards. Let's say it gets downwards by this delta AB, but C can't go upwards anywhere, and since BC have been shortened by this minus something, so it have to be equals to minus delta AB, same amount. अगर ये 5 mm elongate होगा, डेल्टा BC को शॉर्टन होना ही पड़ेगा माइनस दिस डेल्टा AB 6 mm 5 mm जो भी है. Okay, then if we apply this condition, we can say RA L1 by A1 E plus minus P minus RA L by A2 E equals 0, and you have two unknowns here, reaction A. You can get reaction 1 in terms of external load P. If once you got it is a function of P, you got function of P, and once you got reaction A, you can get the reaction B. Reaction B equals P minus RA. From the first equation we write this one, RA minus P RC. From that we can write this one. So we can get the final reactions. This is how we can solve indeterminate structures. Let's take one question on this. Let's take one question. You have a prismatic bar, that is area cross section is constant between two rigid walls. If the walls are rigid, that means the net displacement at the ends, that's the net displacement of the entire member is 0. The member are getting either compressed, one part maybe gets compressed, other part getting elongated, so that the net displacement of the entire member is 0. This is what the rigid wall means, or we can say its support is fixed. So you have here A support, and you have here support B. Let's say at a section 100 mm from A, you applied force of 13.6 kilonewton, and at a section further 200 mm away, you are applying force of 27.2 kilonewton. Question is saying get the reactions at the supports. Find reactions RA and RB. So we can do free body diagram analysis. Would say let's remove the support. You can say this is your 13.6 and this one is your 27.2, and the length between these two is equals to 300 mm. Okay. Let's assume we can assume anything. Assume A reaction at A in this direction and reaction B also in this direction. Let's say reaction A is in this direction RA, and reaction B is also in this direction RB. So by summation of forces in horizontal direction equals to 0, we can say RA minus 13.6 minus 27.2 plus RB goes to 0, keeping this side as positive, this direction as positive. One is your number one equation. Number two equation, since you have unknowns as 2, so next equation we can get from compatibility condition that says delta total or delta net have to be equals to 0. Delta total have to be 0. So for that we need to get the free body diagram for the three for these three sections. Okay, this one is your number one. Let's say here the reaction is RA. तो इसमें पहले थोड़ा सा काटेंगे dx from this point, तो यहाँ पे काटेंगे तो आपका 13.6 इसमें नहीं आएगा. So we will say this one is your RA. It's getting elongated. Then next one is your, अगर यहाँ पे RA है तो इस वाले में RA opposite होगा, and इसमें और एक force भी है 13.6 in this direction 13.6. So the net, assuming RA more, RA is we assume that RA is more, we can say net is tensile of RA minus 13.6. और इस यहाँ पे भी जो है हमने पहले dx पहले ही काटा, इस लोड से dx पहले ही काटा. And for the third one you have this one as RA minus 13.6. In this it had to be RA minus 13.6, and the effect of 27.2, it is in this direction, so we can say this one 27.2. And finally we can say the net have to be, assuming the net to be clock this positive, we can say RA is more. Assuming RA to be more, we can say RA minus 13.6 minus 27.2. So your RA minus, this comes out to be 13.6 minus 13.6 plus 27.2. You get value of 40.8. We can say 40.8. Can say, and their length is also mentioned. Let's say this one is your 100 mm, this one is your 200 mm, and this one is your 300 mm. So now using the condition of compatibility, that is net displacement between the supports have to be 0. That is net displacement between the supports A, B have to be equals to 0. So we can say reaction A 100 PL by AE. Let's say A is constant, E is something we don't know, we don't care about A and E here. RA PL by AE. Next one is your also positive tensile. We can say RA minus 13.6 into L. L is your 200 mm. AE. It is prismatic bar. Its A remains constant with length. And next one is your part 3. That's your RA minus 40.8. RA minus 40.8 L by AE equals to 0. AE goes to 0. AE goes to 0. AE goes to 0. You can say we can solve this equation and get the value of RA equals to 24.93 kilonewton, and value of reaction at B we can get as, by the force equilibrium in x direction, we can get the reaction B as reaction B comes out to be RA was your 24.93, then you do summation and you can get 15.8787 kilonewton. Okay, now we have another question. That's a very important, critical question. The problem number next is you have two rigid bars A, B, and C, D. You have two rigid bars A, B, and C, D. This is your support, hinged support. You have two bars A, B, and C, D. A, B, and you have C, D. Two rigid bars A, B, and C, D are supported by pins at A and C. Pin supports. These are hinge support, or we can say it's pin supports. And the two rods. Determine. We have two rods also. Here, one rod is there, made up of aluminum. So here it's supported here. Aluminum rod. L is 2 meter. You can say 2 meter length. Area cross section is 500 mm square, and your modulus, Young's modulus, is 70 gigapascal. And next bar we have connected here between B and D this way. Length is it's made up of steel. Young's modulus of elasticity is 200 gigapascal. Length of 2 meter, and area is 300 mm square. So the external loading is at point 3 meter from C. It's saying, the question is saying, get the value of P, maximum P, if vertical moment at delta at that point P, if delta P is equals to 5 mm. It's saying get the value of P for which the point P is getting displaced either downwards or upwards. We can see it from the free body diagrams, so that the net displacement at P is equals to 5 mm. Get the value of P. So what can you do? This is also 3 meter. Whenever the question is very difficult, do one thing: cut the sections and do the free body diagrams. Let's start from the CD. This one. This is your CD. Here the support. This pin support does not allow the member to go upwards or horizontally or vertically. It restrains the movement in horizontal and vertical direction, but it can allow rotation. As the door, it can allow theta, so it can rotate. So it will react in vertical direction. So for the P here at mid of the bar CD, your reactions would be P by 2, and this is also P by 2. If at D you got P by 2, same P by 2 have to be transferred to the bar made up of steel. This steel bar, it will also have force of downward force of P by 2. That means it is getting elongated. P by 2. This is P by 2 load. If here P by 2, if here it's P by 2, at point B in the bar AB, you have same force downwards, p by 2. And this is your hinge A. Now we need to get the value of force in the bar, this aluminum bar, at a distance of 3 meter from A. We can say if it's p by 2, it had to be equals to p. We can check it from say summation of moments at A goes to 0. We can say p by 2 clockwise into length is 6 meter. That and your anti-clockwise minus p aluminum. Its reaction r into 3 goes to 0. We can say r comes out to be equals to p. So your r comes out to be equals to p. Once r equals to p, same force has to be transferred. Same force have to be transferred to the bar, aluminum bar of 2 meter. Here it is r upwards, it had to be downwards, r equals to p. Okay, so we have done all the free body diagrams. We need to get, oh my god, we need to get the value of p such that net deflection at point P equals to 5 mm. We need to combine all those effects such that the delta at P equals to 5 mm. So we can do the superposition principle. We can use the principle of superposition here, combining the effect of this bar, how much it can displace, then a b bar, how much it can go downwards, then this bar, then finally this point. So it takes a lot of calculations. So we can get, starting from the top, we can say in the bar made up of aluminum, we can have tensile force. So your delta, it is getting elongated. Since at the top support is fixed, it won't allow to go up. So your bar this bar made up of aluminum have to go downwards by some deformation equals to delta 1. Delta 1 is your p, length is your 2 meter, pl by area is your 500, and e is your 700 into 10 to the power 3 megapascal, gigapascal into megapascal. Then your delta 1 comes out to be equals to delta 1 comes out to be, yeah, we can't get it as of now because you have unknown of p. So you got some function of p delta 1, but it had to get downwards. There's no option for him, for this bar to go to get elongated. It had to go downwards by the same amount of delta 1. See, here the bar connection is rigid. If this point goes downwards by delta 1, so the bar had to go downwards also, because it can't deflect like this. Your aluminum is getting elongated, so it can't go like this way. Not because bar is rigid, so it had to rotate by say theta. From theta it had to rotate so that overall this point reaches to this point and your bar gets elongated. And to maintain the straight continuity, point B have to be shifted to point this one. So this one is displacement at B. So we can say displacement of point B equals to displacement of point B have to be equals to that's from the symmetric triangles. We can say if this is delta 1, delta B have to be equals to twice delta 1. For 3 meter you got delta 1, and for 6 meter you can get twice delta 1. So this one, so till now we got the displacement of delta B. from the bar AB. Okay. Now, since there's also connected this a bar of made up of steel, this bar here, this is made up of steel. So this is getting tensile force, so it's also elongating. So once point B has reached already up to this point, now this bar, steel bar, is also elongating. The steel bar is also elongating. If the steel bar was of 2 meter, this steel bar was of 2 meter. Say this was your 2 meter, and it's getting elongated. If it's getting elongated by amount of delta steel equals to p by 2, length is your 2 meter, area cross section is 300 mm square, modulus of elasticity is your 200 into 10 to the power 3. You got some displacement, so your it had to go downwards by delta s. This is your delta s. Once your point D have been reached to this point, the point D have been reached to this point, so since the bar CD is reached, so the C have to rotate by some theta in order to maintain the slope. So your displacement at delta P, we know already, delta P equals to, we have limited it to 5 mm. Delta at P have to be limited to 5 mm. If it is 5 mm for 3 meter, and so delta at D have to be equals to, this part have to be equals to 10 mm. So this is your condition, that delta at D equals to 10 mm. That's 2 times delta P. That's 2 into 5, 10 mm. Once you got this, you say how much delta D have been displaced. How much delta D have been displaced? That is equals to how much this bar have been shifted down, plus how much this the bar which was in the middle of made up of steel have been elongated. Uh, that part is also have to be encountered. So delta, I would say delta D equals 10 mm. It has to be equals to delta B. This one, delta B. Do we get delta B? Delta B is twice delta 1. Twice delta 1 plus, and the elongation of bar, steel bar, that's equals to delta S. So once you deploy the results of delta S and delta 1, you can get the value of P, and that comes out to be equals to 76.4 kilonewton. Rest calculation you need to do it by yourself. It was a very crazy question. Now next one is your, firstly removing this all stuff. Next question, it says this is your initial condition. Initial condition is you have hinge support here and a bar, stepped bar of say 300 mm. Then its cross sectional area increases to from 250 mm square to how much, 400 mm square, and the length of this part is your 300 mm also. And the external forces are acting at a distance of, one is your 150 mm. At a distance of 150 mm, your external force is acting equals to 300 kilonewton. 300 kilonewton. And similarly, in the next bar, at a distance of 150 kilonewton, this one is also 150 kilonewton. Yeah, 150 mm. your force is how much? 100 kilometer. So, but there is also one thing here. Here is the, let's say it's ground or anything. So this one is available. This part is delta available. If let's say because of these two tensile forces, of these two forces, external forces, it might elongate. So it can elongate. We don't know how much it can elongate. If say it elongates, but delta available is only this much. Delta available equals to 4.5 mm. So this is your clearance. You can say it's your clearance. It can elongate up to this point. After that, it won't elongate. That extra part would be uh, restrained. So we can treat it into two separate. We can think it in a separate ways. Assuming that number case one is your case one, that assuming no this clearance was there. We say that no support here. It is a support Z. No Z was there. No Z was there. If no Z was there, it can freely elongate your bar can freely elongate. We would say how much elongation it would be having. So for that, we can say we can do free body diagram analysis. See for the so we can have free body diagrams. So for the first 150 mm, let's say assuming they say reaction at A, the reaction A is upwards. The reaction A is upwards, or A is your reaction A upwards in this part. It had to be downwards in this part. And for the next 150 mm, you are having a force of 300 kilonewton also there, and you have reaction A upwards. So the net comes out to be, assuming Ra more, would say Ra minus 300. And in the this part one, this 150 mm part, I would say this is your 150 mm part. Here the no forces acting, मैं dx पहले ही काटेंगे तो आपका this one comes out to be Ra minus 300, and this one is Ra minus 300. Okay, and in the last part, that is this one. तो इसमें आपका 600 भी आ रहा है, and a reaction of Ra minus 300 upwards. And here there's no reaction. It's free. In this part, it is free. So, but the thing is, if we do summation of forces in vertical direction, I would say summation of Fy goes to 0. So your reaction at A comes out to be upwards, as we assumed. That is correct. 300 plus 600, that is 900 kilonewton. This one plus this one. This is your 900 kilonewton. If Ra is 900 kilonewton, which implies this is your 900 kilonewton. I would write it as this is your 900 kilonewton. If it is 900 kilonewton upwards, it is 300 downwards. So net is your 600 upwards. It had to be 600. So it's your 600 minus 300. Net comes out to be 300 upwards, and minus 600 downwards. So minus 300. So downwards minus 300. This minus 300. But in this part, there's no one to balance this 300. If let's say assume we say that at the top there is net 300, but in the downward part there is no one to balance because the side is free. So that this means nothing. So we can say the reaction here, internal force in this part, last part is 0. It had to be balanced. There's no one to balance in the external part, this end part. If it was internal section, there might have been internal force, but it's at the end there won't be any force. So we know RA equals 900. So net this comes out to be 600. Comes out to be 600 positive, tensile, and tensile. We can get the total displacement. How much a how much total displacement of the bar would be, that we can say that comes out to be, in the case 1, delta total comes out to be let's say first one is your 900 kilonewton, keeping the kilonewton common, keeping that common, I would say 900 kilonewton. L was your 150 mm. L by area cross section of the first part was your 250 mm square. L by A. E was your gigapascal, 200 gigapascal. And this is a tensile, so it is positive. Next one is your net 600 plus 600, and same length is also there for this part, 600 into L mm. L by A E. And third part, your area is different. Your area comes out to be, that's 400 mm square, and the net force acting in this third part is your 600 kilonewton. 100 kilonewton into length was your constant for 150 mm, and gigapascal, 200 gigapascal. Then you calculate total deflection, total displacement. That comes out to be 5.625 mm. But if you see how much was the clearance, the clearance was only 4.5 mm. If the clearance is only 4.5 mm, the body would try to expand, elongate. How much? Body would try to elongate 5.625 mm, but the clearance is only 4.5 mm. So the we can say delta prevented, the deformation that have been prevented, is equals to 5.625 minus 5.625 minus 4.5. This amount of displacement or elongation have been prevented. How much it comes out to be? This amount, 5.625 minus 4.5, 1.1250 mm. Because of this part, since you are preventing strain, you are not allowing this to happen. Because of strain developed, there would be strains developed, internal forces would be developed that will give you internal stresses. So stress will generate after 4.5 mm have been elongated. Then after that, stresses would generate. But the question was saying what is the safe load? Determine the reactions at A and B. Okay. Yeah. Determine the reactions at A and Z. Question was determine the reactions at RA and R at Z. Reaction A and reaction Z. We know initially reaction A was, in the case for reaction A, it came out to be 900. Yeah, reaction A came out to be 900 kilonewton. And in the next case, and in the first case, your reaction Z was 0. Now our compatibility says, see, after the bar has elongated, after bar elongated, how much clearance? After bar elongated 4.5 mm, that is your gap clearance. After it reached the clearance, there was a support Z. there was a support Z, so the bar became fixed now. So the configuration looks like this one, case B. Actually, it was this way. Actually, it was like this. Now the configuration has become like this. This is your support Z, this is your support A. Here is your load 1, load 2. So now we need to get the value of reaction A and reaction Z. Now assuming reaction A upwards, assuming the reaction A upwards, we can also do now free body diagrams. Assuming reaction A upwards and reaction Z also upwards, we can do free body diagrams. I would say this one, reaction A upwards, and it had to be reaction A up downwards, and the force was here 300 kilonewton, it was 600 kilonewton. So in the next part, it had to be downward 300, RA upward. Net we can keep upwards, RA minus 300. Okay, next one is your part 3. We say RA minus 300 was upwards, RA minus 300 was upwards, and it had to be here RA minus 300 upwards. हमने इसमें dx पहले ही काटा. So in the next part, last part, it is RA minus 300 upwards, but downwards is also acting minus 600. So net comes out to be say positive. We don't know the value of RA, we can say it's more. RA minus 900. So applying the compatibility condition, we can apply the compatibility condition now, because supports unknowns are 2 and you have only summation Fy comes out to be 0, because RA plus RZ comes out to be 900. You have 2 unknowns, so for that used compatibility condition, that that the compatibility condition says that the deflection caused because of these four free body diagram would be 0, isn't it? Just wait for a second. So this part we can also we can solve this in other approach also. A compatibility condition, we can use that. We can say in other way that the clearance that is prevented, the delta that has been prevented, this delta is prevented because Z has came into effect. Support Z has came into effect. So the reaction at Z is restraining how much deformation. The Z support is not allowing this part of deformation to happen. So if you write compatibility condition in terms of Z, we can get the value of reaction Z, and accordingly reaction A can be solved in the case 2. Say this was your bar, then your support Z. So we can say this was your 300 mm and this was your 300 mm. When we say redundant, we in indeterminate structures, when the forces are more, unknowns are more, one of the we keep one of the forces as unknown, that we say that as redundant. It is a redundant support or reaction. Redundant reaction. So for that, so for now, that was your redundant reaction. So because of the redundant support, how can you solve the redundant? You write it this way: solving redundant. For solving the redundant support, solving for redundant reaction, what you can do, you have to remove the external loads. Remove all external loads. Then just just apply the reaction itself. Apply only reaction Z on the member. No other force should be there. Only checking the effect of this reaction Z on the member, total member. And we know because of this RZ, it's preventing how much deformation? 1.1250 mm. We can say in the free body diagrams, we can say this one and this one. Say the reaction Z is upwards. The reaction Z is upwards, RZ. It has to be RZ. So it's compressive because it is preventing this part. And say it is RZ and it is RZ. We can say for the first part, length was 300 mm. We say RZ minus RG into 300 mm. Area cross section was 250 mm square. And the modulus of elasticity was 200 gigapascal plus. In the second part, you have minus RZ. Length was 300 mm. And your area was 400 mm square into 2 into 10 to the power 5 Newton per mm square. Then we know that this deflection and this deflection, these are equal to the deflection prevented, that is equals to 1.1250 mm. So you can solve the result now, can get the value of RZ, and the value of RZ comes out to be equals to 115.4 kilonewton. Once RZ is known, we can get the value of reaction A, that is 900 minus RZ equals to 784.6 kilonewton. Hope you understand question. Yeah. So this was the end of this concept. Next concept will be a composite bar. Maybe in the next lecture. Yeah, I think in the next lecture would be dealing with the composite bars and the temperature variation problems. See you next time. Hope you enjoyed the class. Goodbye, everyone.